there exists this rather concrete, overarching, simple algebraic formula on which we can understand the analytic continuation of those formulas. We can understand those power series as analytic continuations of one another. The larger program of analytic continuation, maybe you don't have the f of z is 1 over 1 minus z. Then it's more challenging. The thing that's global and well-defined everywhere is the 1 over 1 minus c function. That is the thing you want, that's everywhere. The power series just gives us a local description of that.
Okay.
But now, I was not looking for everyone to say all of that in their solutions. I just was looking for some subset of that. I wanted you guys to do some soul searching about what that means is all. Oh, I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask that you just guide our steps today, help us to understand a little bit more about the proof of the inverse function theorem, if we can, and perhaps something about normal and tangent spaces, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me try to speed my way through this next bit here. There is something I need to say because I said something possibly false. Well, I don't think it was false. It kind of depends on the finer points of what exactly I said Monday. I don't remember exactly what I said, and I certainly haven't reviewed the tapes. So, like, I'm not 100% sure. I may have said something along the lines of the inverse function theorem. I may have said something along the lines of, if I have a function, all right, and well, I gave the example of this example, right? F of x equals x cubed, right? If I set that equal to y, I can solve for x equal to the cube root of y, right? Which you could say is f inverse of y, all right? And so I said, well, and here, by the way, we have f prime of 0 is equal to 0, yet, you know, f is invertible. Near x equals to 0. In fact, everywhere. I was like, well, there, you know, that seems like a counterexample to the sort of the converse of the inverse function theorem, but I have to be careful because there actually is a, well, let's just look at it. So suppose, you know, consider f a mapping from Rn to Rn, and let's suppose that f from U to V is bijection, okay? And x naught is an element of U, all right? In other words, there exists the local inverse for f, and x naught's a point in there, all right? Then there exists f inverse, a mapping from V to U, right? And in particular, we have that f composed with f inverse is the identity map on V. And we also have that f inverse composed with f is equal to the identity map on U. If it's a bijection, we have these things, right? Okay, so if in addition we have a continuously differentiable, and honestly, I don't even know, I probably don't even need to slap the continuously in here. I probably could just settle for differentiable. I think that would be sufficient here to make my point. Well, if that's the case, I probably don't need, let me just, I sometimes just tack that where I don't need to. Let's not. Just differentiable. All right? If it's a differentiable bijection with differentiable inverse, all right? then of course this is just the set theory of it. But if it's differentiable with differentiable inverse, then what else do we have to have? We have the chain rule. And what does the chain rule tell me? Well, the chain rule tells me I can differentiate this. And what I get, among other things, is that the differential of f composed of the differential of the inverse of f is equal to the differential of the identity. But the differential of the identity, once I was researching, and like me and my advisor, we got really confused because we inadvertently got trapped into the thought that the identity is constant, so derivative is 0. It's like, oh, no, not 0. Identity. So the best linear approximation to the identity is, of course, the identity. You know, I mean, duh. Yeah. Or it was the other. I know we got. There was this. I know, and then all of a sudden, like the the confusion cleared, and we were just like, oh man. But it was probably my fault. Let's see here. Anyway, so it likewise. So, what does that say? That says that that says that the determinant of, the differential and the determinant of the differential of the inverse have to be equal to 1. Which means it means that you cannot have derivative 0 and have an invertible map. So, explain to me my counterexample.
So say inverse function.
I'm not even. I mean, we haven't even got to the inverse function theorem yet. I'm just assuming that I have an invertible. I'm assuming that I have a function that's differentiable with differentiable inverse. And I'm showing you that a necessary consequence of that is that the product of the derivative, the differential, and the differential of the inverse, and likewise the Jacobian matrix. So like the Jacobian matrix of both the function and the inverse function, they must both be invertible. In fact, they have to be reciprocal because their product is 1. How can this be? Because I have an example up here with an invertible function, right? And the derivative is 0. And yet the function's invertible. What gives? I mean, isn't f of x equals x cubed differentiable everywhere? Okay. What about the inverse? Is this differentiable everywhere? Not at 0, that's right, because notice that the cube root graphically looks like this, right? This is y equals to the cube root of x if I flip back to, like that. But notice that the derivative with respect to y of the cube root of y is exactly 1/3 over the cube root of y squared, right? And so that is not invertible at 0. So my counterexample is actually not troubling to this calculation because it doesn't even fit into the preconditions of this discussion. So this is in Edwards, and when I first looked at it, I was like, Edwards has a mistake, and I was like, whoa, no, careful. That function is not. So that's a good example. Here's an example of a function which is everywhere differentiable, everywhere invertible, with an inverse which is almost everywhere differentiable except for one stupid point. But on the other hand, there's a certain beauty to this example, right? Because while the derivative is technically not defined at 0, it's infinite there. So you have infinity here paired against the 0 there. So intuitively speaking, it's still kind of simpatico with that. I mean, it's not too bad. Okay, so there's that. So yeah, let's state the inverse. Let me state the let me set up the theorem and then state it if I can. So we're on page, roughly speaking, 182 to like 184 probably of Edwards. C.H. Edwards, Advanced Calculus of Several Variables. So he starts by talking about a C1 mapping on Rn and F. And he says, okay, so he says, what does that mean? He says, the inverse mapping theorem asserts that the continuously differentiable mapping is locally invertible in a neighborhood of the point A in Rn if its differential is at A is invertible. So this is basically the theorem. F is locally invertible at A if the differential I guess I put the A here. Differential at A is invertible. This is not an if and only if either, right? I mean, anyway. Let's see here.
So being invertible means that the determinant is not zero, which corresponds to the calculus one.
Yeah, right. So he actually characterizes it as df1 a of x equals to y1, df2 a of x equals to y2, df n a of x equals to yn. So you got these linear equations have a unique solution for each x in Rn. Have any for each y in Rn. What's that?
Are those a component function?
Yeah, those are the component functions.
That's a characterization.
Well, we're getting there. This is not the theorem yet. He's explaining what it means to this invertibility of the differential would mean that this system of equations has unique solution x for any given y, right? That would be invertibility of the differential, right? And he says, okay, then he starts trying to state the theorem. He says, if you have this, then there exist neighborhoods U of A and V of F of A, which we'll call equals to B, all right? Such that the equations f1 of x 1 through xn equals to y1, the fn of x1 through xn equals to yn have unique solution x for any given y in V, I suppose. And where does the unique solution x have to be coming from? In U. All right, so this is the theorem that there exists a neighborhood an open set of A, an open set containing A, and an open set containing B, which is the image of A under F, such that you can invert the equations for F and solve for X in terms of the Y.
And that's because it's 1 to 1.
Yeah. Well, that's the claim. We don't know why it's true yet. And then at this point, Edwards goes through the calculation I went through on the other board. He says it's easy to see invertibility for the differential is a necessary condition for local invertibility of F near A, because the composite of the function and its inverse are equal to the identity, and the chain rule then says that the product of the differentials in opposite order have to be the identity mapping of Rn, right? And then he's like, well, that means the derivative matrix must be invertible, blah blah blah. Now, so like, I don't know. I'm not entirely convinced I'm not entirely convinced he's ruled out my counterexample still. Like, I don't see. Well, let's just go on, and maybe his careful statement of the theorem is upcoming still. You know. So one thing to notice before, and this is like just a more kind of like complex analysis comment, is local invertibility need not guarantee global invertibility. You know, like we have. Well, he gives the example of the square mapping and so like f of if you look at f of z equals to z squared, you know, then this mapping has f prime of z equals to 2z, which of course is not equal to 0 if we look at like for all z in the punctured plane, if you'll allow me to skip over to complex variables for a second here. And so like that means that it's got a non-zero Jacobian, right? It's, as we've talked about in the other course, conformal, right? But more to the point here, it's got an invertible Jacobian at each point, and yet you can't have an inverse extend all the way around because this mapping, you know, it is not one-to-one globally. Like, I mean, obviously, if you, I mean, for one thing, you know, well, anyway, he looks at the formula in polar coordinates. He's like, this in polar coordinates looks like this, right? He says, from this it follows that f maps the circle of radius r twice around the circle of radius r squared. So it takes a circle, it takes a disk, right? And then it maps it, it covers, it takes the disk, it takes like the disk of radius r, and then it twice covers the disk of radius r squared. Which means it's a 2-to-1 map. Which of course then means it can't be like globally 1-to-1. You're going to have to restrict it down enough so that, you know, you don't run into that global issue. And of course that's part and parcel of the discussion of like how to choose a branch cut for like the square root or the principal square root and all that jazz. So anyway. that's another direction to think about this theorem. It's a local theorem, right? Local. Now, so let us begin with the proof, and hopefully the proof will, as we're working through the proof, we'll understand, because I think Edwards tends to have like an intuitive discussion of the theorem before he has the careful discussion. So let's not be too critical of him not addressing my example just yet. It'll probably get addressed in the as we go on here.
Are we going to prove the theorem itself? Or
Yeah.
characterization?
I'm going to try to at least sketch the proof. So the proof has a couple different parts. One of the parts is a lemma. Let's see here. So he says, we now begin with the proof. This is on page 183. We now begin with the proof of the inverse mapping theorem. It will be convenient for us to start with a special case in which the point A is the origin. So he's basically going to prove a lemma. Prove in case. Which case are we going to prove it for? We're going to prove it for the case that f of 0 is 0. All right, that's pretty nice. F prime of 0 is equal to the identity. Well, that's also pretty nice. And also the pointing consideration, well, that's already here, but the pointing consideration is 0. All right. And the lemma says the following. Here we go. Let f from Rn to Rn be C1 mapping, and that means differentiable with a continuous derivative. That's continuously differentiable, such that f of 0 equals to 0, and d f at 0 equals to the identity map. Suppose also that the norm of the differential at x minus the identity map less than or equal to epsilon less than 1 for all x in C sub r. Now remember what C sub r was? So in the current context, that would be I believe this would be like minus r to the n power. It's the r cube centered at the origin, which was the unit ball in the soup norm that we talked about. All right, then the cube of 1 minus epsilon r is a subset of the image of the r cube under f, which is a subset. And I don't remember in Edwards if he does subset or equals to, or if he does strict subsets. You know, some books, they just write subset for subset or equal to. For me, if I'm left to my own devices, I just write subset or equal to when equals possible, and I write strict subset when equals not possible. But there is disagreement on this issue in different books, yeah? Like a lot of books, just for the sake of typesetting, just have subset. And I don't remember off the top of my head what the rule is in this book. Man, give me a second here. That's not up. Where does he do his set theory? Does he? Do 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 do. Well. I'm going to assume that this has my usual meaning. So then C, hopefully it won't be an issue, 1 plus epsilon r. I mean, he doesn't have this in the book, but I don't see him writing that with the equality. I guess it has to be not equal anyway. Let me just leave it. It's fine. All right. Moreover, period. Moreover, if V is equal to the interior of this one, the 1 minus epsilon r cube, and U is equal to the interior of the r cube intersect with the inverse image of V under F, then F from U to V is 1 to 1 and onto and the inverse G from V to U is differentiable at 0. Okay, so far this has nothing to do with my counterexample because we're assuming that the derivative at the point in question is invertible, right? So if whatever my counterexample might have to do with anything, it's not relevant here. Yay! And what else? Finally, continuing here, the local inverse mapping G from V to U, all right, is the limit of the sequence of successive approximations which will denote G sub m equals 0 to infinity, defined inductively on V. How do we define them inductively on V? Well, by G sub 0 of y equal to 0 and G sub m plus 1 of y equal to G sub m of y minus f of gm of y plus y for y and v. All right, there's the end of the lemma. That's quite a lemma. So what this lemma really is just, it is the inverse function theorem in a special case. And once you prove this, then you can just basically like move the theorem elsewhere and still have it be true. All right, you can essentially just kind of like just, you know, lift the theorem wherever else you want to go. That's the argument that's given next. This lemma is the heavy lifting for the theorem. It's really where the interesting part is. All right, so let's look at how do you think we're going to prove it? So I won't, I guess I won't belabor this part much. Like, he says we've already shown that this is a subset of that in a previous corollary, and it follows from the proof of the corollary 2.8 that f is 1 to 1 on the R cube. Excuse me. Now the corollary that he's referring to is from the previous section, where that was something that was so the corollary 2.8 is actually if you have a continuously differentiable function at a point, and if you have that the differential is 1 to 1 at one point, then the function itself must be 1 to 1 on a neighborhood at that point. So that's what corollary 2.8 was. Corollary 2.7 is literally an estimate about the R cube. Like, corollary 2.7 is pretty much this, and I don't want to get into all of that, if you don't mind. I'm trying to not do everything here. All right. He says, so apparently the sticking point is showing that this, like he says he needs to use the contraction mapping to prove this part of it, that the 1 minus epsilon times R cube is a subset of the image of that. So I really wanted to mostly look at the contraction mapping part of this, so let's do that. So what he does on page 184 is he defines phi. So here's a very small part of the proof, all right? I mean, admittedly, to really do this proof in class, I'd probably need like 3 hours, right? Because there's a lot of build up to this, truthfully. But this is the heart of it. So he defines phi so for given y in this 1 minus epsilon R cube, all right, he defines an alleged contraction mapping, and here's what it is. Phi of x is equal to x minus f of x plus y. He says we want to show that phi is a contraction mapping of the R cube, and its unique fixed point will then be the desired point x in CR such that f of x equals to y. Let's see that. Let us first study, supposing this is a contraction mapping, what would its fixed point be? If we had phi of x equals to x, that would be the fixed point condition, right? And if that was also equal to x minus f of x plus y, well, this equation right here precisely says what? It says that y is equal to f of x. So the fixed point of this contraction mapping is exactly giving us the x in the it's going to end up giving us the x in the R cube, which maps to this y over here. So we're essentially picking a y in here, and it's showing you that you can find an x. It's going to show us you can find an x in here such that y is equal to that f of x, which would then prove that this is a subset of that. So the question then is for here, well, the rest of the setup, right? Because I haven't quite set it up yet. Remember, the contraction mapping has to be done. I told you that the contraction mapping, so this isn't That's not the end of the story. Because we want to show that, I mean, this is generally fine. This is whatever, but that's not actually where it's not supposed to be a contraction mapping on our end. That would be nonsense. The claim is phi is contraction mapping on CR. Okay? So we just need to look at seeing if we can't well, I'm just going to follow the calculation of Edwards and see if we can make sense of it, okay? So here's what he writes. Let's see if we can understand it. He's like, so he's applying corollary 2.6, which I'll have to look at in a second here, okay? But what's corollary 2.6? Just a second. Oh, corollary 2.6 is the multivariate mean value theorem. So he starts by applying the multivariate mean value theorem to write the following. He says this is less than or equal to the f of x minus y naught, excuse me, not minus y naught, there's no y naught there, f of x minus x sub naught plus the given y sub naught. Now I think that's nothing. What is that? That's not the theorem at all that I was just talking about. What is this? This is equal to that plus that, right? This is just triangle inequality for the norm in consideration here, right? The next step is the multivariate mean value theorem. Here it is. This is equal to the norm of f of x minus f of 0 minus df of 0 acting on x minus 0 sub 0 plus this. I think I'm still getting ahead of myself. I still have not yet applied the multivariate mean value theorem. Okay, still haven't done it. This f of 0 was what? 0. And the differential at 0, the identity, right? So all we're looking at here is minus 0, and that is exactly that. Still, nothing interesting has happened yet. This is just applying the data. Maybe the next step will actually apply the multivariate mean value theorem. Check this out. So this is less than or equal to the norm of y sub naught plus the norm of x sub naught max of x in the r cube of the norm of dfx minus df naught. df 0 really. That is the multivariate mean value theorem there, because I'm the multivariate mean value theorem, if you look at it, it is literally replacing this with the max over x in L of dfx minus lambda, where lambda is the, like, I forget what lambda is, but rats. But the point is, this is done over like a line segment. I can't read upside down, but lambda is a linear mapping. Oh, it's done for, so it's the corollary 2.6 is done for a linear mapping. This is playing the role of the lambda in the linear mapping, and it puts dfx minus lambda, and it's done over a line segment, but if I remember right, oh no, Well, no, yeah, it's a line with endpoints a and a plus h, but the thing is, I think you can think about, I mean, certainly CR is full of line segments, so I don't know. There seems like a little bit of a, maybe intuitive but not unreasonable jump there. I don't know. Oh, I lost my point in the proof. Let me back here. Just a second. All right, so this is then less than or equal to 1 minus epsilon times r plus r epsilon. So this epsilon is part of the preconditions of the lemma, right, over here. That's this coming up right there. And the r is coming because, remember, x is an element. X here is an element of CR. And what follows? So x being an element of CR means that that literally means that this is straight up equals to R, I think. Oh, wait a minute, no, CR is not the boundary of CR. It's the solid. It's not just the skin of the R cube. It's the whole thing. So it is an inequality that could be at most R given there. And of course, then this is just equal to R. So what does that show you? That shows you that if x is an element of CR, then guess what? Phi x is also an element of CR. This wasn't even an issue in our previous contraction mapping arguments. Like into was like trivially true for whatever we were looking at. I forget exactly, but like this time, just proving that phi, and so this all just to show that phi is in fact a mapping from CR to CR, right? All right. And then he says, to see that phi is a contraction mapping, we need only note that. So the contraction, so this is actually, I wish I had just not done, I'm sorry, I shouldn't have done this. So can we see that phi is a contraction mapping? Oy, oy, oy. I was tired. Ay, ay, ay. So we should do what? We should look at like phi of x. How's it go? Phi of x minus phi of y, I guess. Man, but y's got a fixed and arbitrary meaning here. Why do that? Goodness gracious, that's not. I want to do phi of x1 minus phi of x2 if that's okay with you, Ernesto, because like putting y there, that I don't get that, because y has a fixed but arbitrary meaning here with regard to the contraction map. Like that's a fixed y here. You shouldn't use also y for the input to the contraction mapping. That's weird. I'm not that with it, but I know that that's not a good notation. All right, so then, this is what? We do x1, right? Minus f of x1 plus y minus x2 minus f of x2 plus y, right? And as you can see, there was no danger for confusion because the fixed but arbitrary y that's defining the contraction mapping cancels, and you're just left with x1 minus x2 minus parentheses f of x1, or well, I guess you could just write, I don't know, whatever's best here, plus f of x2 minus f of x1. And then what does he do? He's like, okay, well that is less than or equal to epsilon by 1. Whoop. What? Hold on a sec. Say what? So now apparently this is corollary 2.6. I'm sorry, I guess so corollary 2.6 says that that's less than or equal to, where'd that stupid thing gone to? So that's actually, we could do f of x2 minus f of x1 minus parentheses x2 minus x1 like that. That's more how he has it formatted. And then he's like, that's equals. And then this is less than or equal to, by corollary 2.6, epsilon times x1 minus x2. Now he has x and y rather than x1, x2, but, and then that makes it a contraction mapping because the epsilon here is less than 1 by construction. So phi is indeed a contraction mapping with contraction constant epsilon less than 1, therefore has a unique fixed point such that f of x equals to y. All right. And then he constructs the inverse by a sequence of functions, just like we talked about last time. And then he has a proof on page 184 to 185, which proves the differentiability of that sequence of functions. And then, theorem 3.3, he takes this lemma and he does it instead of at the origin, he does it at an arbitrary point where the derivative, where the matrix is non-singular. Then he gets local invertibility with respect to some neighborhood of that point. And the proof is basically just using the lemma with a translation from the origin to A. Because the translation is, a smooth map it's an invertible, it's a bijection, like plus minus A, that's a, infinitely differentiable map with a smooth inverse. And so you can basically take the function that you're given with the data that you're given, and you can convert it to a function that's like lemma 3.2, and in so doing you can prove the inverse function theorem. But it's about a page and a half of details. So anyway, I wanted you to see what's involved, and maybe you'll have a good analysis course in grad school where you do these things carefully perhaps, but even if you never do, I think it's important for every math student to know about the basis of our existence theorems. See, like the inverse function theorem, it involves this kind of logic. There are versions of the inverse function theorem which don't involve the contraction mapping, that just basically involve like playing epsilonics with, it's kind of more like the proof of the inverse function theorem that you see in my complex notes, where I'm more, well, that one is, I just stole this one, but there is a way to do it with just kind of like estimates on the range and the domain, and studying how the continuity forces things to be close in the domain to go to things close in the range, and vice versa. And those kinds of careful estimates can be made, but I think the contraction mapping type argument is really the proper way to do these things. And also, this method of argument is the same method of argument that's used, for example, to prove like the Picard iteration converges. It lies at the base of like the existence and uniqueness theorem of like differential equations, things like that. So,
would it be helpful to write a rough outline of all these big theorems?
No, if you want to, but I don't think it will matter to this course at all. I just want to give you a flavor of it, and I think I've wasted enough of your time at the moment. I want you to know about it so that if you're ever in, like, suppose 5 years from now you're working on some research problem, you end up in analysis and you want to you find out that you need to prove the existence of something, and it doesn't quite fit the standard theorem. Well, this is the method that you could try to wield against your problem. I mean, that's more or less what I did to prove an existence theorem in the context of like the A calculus. It's a contraction mapping argument. I actually found it in the end of your differential, oh wait a minute, you didn't take differential equations, but in the differential equations book we use here, Nagelshaft and Snyder, there's an argument by what's called the Picard iteration for the existence and uniqueness theorem. And like, so I was able to take that and sort of do it in the A calculus to prove an existence and uniqueness theorem for differential equations over an algebra. That's why I'm doing these things. Not because you don't need to know every jot and tittle right now. That's not the point at all. The point is to be aware of the method of argument. Okay. And that's about all I can. That's the best I can do for you at the moment. But
I feel like if I don't write some of these things again, like thinking through them, I'll completely forget.
That's okay. That's okay, because to really understand it, you'd have to work through all the corollaries. Yeah. You know. Okay. But hopefully, you will not forget that the theorem itself says that if you have a function, right, on Rn, or ostensibly on an n-dimensional vector space, and you want to prove, and you want to know if it's invertible close to the point, well then you just check the Jacobian, right? Or you could check the differential. And if it's invertible, then, and the function's continuously differentiable, then that means near the point, it has an inverse. That you can remember. Yeah. Yeah. And that's really more the point. Now, so let me talk about one thing here. Suppose you had f, right? A mapping from a vector space to a vector space where, you know, the dimension of v is equal to n, and f is, you know, Fauché differentiable with continuous partial derivatives, all right, with respect to some basis, you know. All right. Then, if you know, f prime, if the differential of f at x naught, right, is invertible, then guess what? F is locally invertible at x naught. So my claim to you is that if we have the inverse function theorem for Rn, right, which I've showed you like a full 20% of the proof of it, right? This is 20% more than you'll see in any other course here, so it's okay. But well, if you know that, then you can do this. So let me show you how it goes. Like, you draw a picture. So something like this. Here's v, right? Here's v again. You have f, all right? Now, I have coordinate maps. My coordinate maps are in fact smooth bijections. They're differentiable with, differentiate them as many times as you like. They have differentiable inverse. I haven't proved it, but you could. We're keeping it real here, so we're looking at Rn down here, all right? So dfx naught is invertible. That means that, I mean, I can look at, okay, fine. So I suppose that the way my formalism is at the moment, that dfx naught is up here, isn't it? Because my differential was, again, a linear transformation on the vector space, right? It's the best linear approximation. It's still up on the vector space, right? But this being invertible means that I can look down here at the matrix of that, right? With respect to the beta basis. So if I have invertibility of this, I get invertibility of that. And you see then, let's see here, and let's see here, what else do I need? What's the mapping down here, from here to here, that I want to think about? I want to. It's a little bit different than that because this is not a linear map. So this is not like linear algebra. This is something a little bit funkier. What I'm doing here is going back up like that. So I want phi beta composed with f composed with phi beta inverse, right? That, let me call this thing G for the sake of discussion. Notice that G is a mapping from, well, from Rn to Rn. But you can sort through it and get that the differential of G is in fact the differential of phi beta composed with the differential of f composed with the differential of phi beta inverse. But the thing is, those are linear maps, so that the differential is just the map again. Which then means that then that means that invertibility of f automatically gives me invertibility of g at the point in question, which means I can apply the inverse function theorem to g. And once I have a local inverse for this g function down here, then I can just take whatever the, it's going to have the inverse function theorem gives me a u here, right? And it gives me a v here, on which g g from u to v is a bijection, right? Not just that, it's a bijection which has a differentiable inverse as well. That's in the proof in Edwards. And so then I just take that and I lift it back up here. And that would to get that, I would just do phi beta inverse of u. Maybe I call that u tilde. And likewise over here, v tilde phi beta inverse of v. And then I can argue that in fact f from u tilde to v tilde is a bijection. It's invertible. And in fact, I can even write the formula for this, the inverse of f, in terms of the formula down here. So I even get access to all of the iterative goodness of the Edwards proof if I just want to lift it up. So once you prove the theorem for Rn, because coordinate maps are so nice, we can bring it up there. This method of argument I'm using right now is really manifold theory. So that's what we're going to do a lot more of. Like next semester, everything is done through that thinking. It's all done through that thinking. But the the coordinate maps in linear algebra are the first and most important example of coordinate maps. It's just that the coordinate maps in manifold theory are, a little bit tougher. Oh, this is wonderful. This is a great place for us to start again.